In the shortest remaining time first, we have the burst time, the criteria, and it is also a preemptive. So at any point of time, if we'll find out a process with the least burst time, so we can take that particular process into the CPU, and whatever process is running, we'll take it out and put into the ready queue. The problem of starvation, which was there in these two scheduling algorithm, would be solved using shortest remaining time first algorithm. Now here we know that how we'll find out the burst time of any future process. We might use the exponential averaging algorithm for that, and we can get the burst time of any process, and we'll take that particular as a reference. Maybe it is wrong, maybe it is right, but it is not exact, as I told you. Without execution of that particular process, we cannot find out the burst time, exact burst time. But this exponential averaging algorithm will give you some sort of approximate burst time for any process. Now let's go to this particular scheduling algorithm. We'll see this scheduling algorithm today. Now for that, let's go to the slide. So today we are going to see shortest remaining time first algorithm. So as I told you, what we have in the shortest remaining time first, in the shortest remaining time first algorithm, we have the criteria of burst time. If burst time is same, we'll take the arrival time for the tiebreaker, and it is a type of preemptive scheduling. Okay, so it is a preemptive scheduling, and let's see this particular algorithm in detail. Now this is one example where we have some processes. Arrival time is given, and we have some burst time which is also given. Now if we see that arrival time is there and the burst time is also there, let's go and find it out, this how this shortest remaining time algorithm works for this particular scenario. Now for that we require the Gantt chart. So Gantt chart we have to create. This Gantt chart will tell us that which particular process is in the CPU and how much time it is taking for the processing. Now a Gantt chart has been created. Let's say we'll create a new Gantt chart. It is already created. We'll create a new Gantt chart here. This is my Gantt chart. Now let's see at time t0, this is t0 or the zero time. What are the processes that are available? So at that particular time, we have only one process available. If we have only one process available, we doesn't have any another option. In the time t0, we have to put P1 into the CPU, right? Because we doesn't have any other option. Because only P1 is available at time t0. And we cannot compare only with one burst time with another, right? Because we have only one. So anyhow, we have to take P1 into the CPU for at least 1 unit of time. After 1 unit of time, we'll see that how many processes are available. So we know that arrival time of 1 is there, like P1, P2 is also joining P1 at time t1, and the burst time now it is available is because already one burst time has been done, so 7 is left. Now 4 and 7, because P1 and P2 only available at t1, so we have an option of comparing. We can compare it and we'll find out that P2 has a chance because it is a smaller one. So P2 has a chance to get into the CPU. Now P2 will get into the CPU, right? And we have, it will go up to 2, right? So up to 2 it will be go. So let's say it is time T2. At time T2, we have another process which are available, which is called P3. Now at this particular time, P2 has already been exhausted one burst time. So 3 is remaining here. P3 has joined. So P3 has a burst time 9, right? So right now, which is a shortest one? So we know that which is the shortest one. So this one is the shortest one. So P2 again will be processed for another minute of time. Let's say T3. At time T3, P4 also join here. Now we have 4 options. Now because one more has been exhausted, so the remaining is 2 here. Now we'll compare P1, P2, P3 and P4 to find out which is having the shortest burst time. You'll find out that it is 7, it is 2, it is 9 and it is 5. So the shortest one is again P2. So P2 will go on for the execution. And so we are not removing it, okay? We are just, scheduler will see at that particular time that how many other processes are there in a ready queue which has the least burst time, right? It is not going to remove it. It will remove, like P1 has been removed. Why? Because it find it out that P2 is a process having the least burst time. So you see, here it is 1, here it is 2, here it is 3, remaining is 2. It will run up to 2. It means it will go up to 5. And after 5, this P2 will be done. It will be terminated. It will remove from the ready queue. Now, what are the processes that are available in the ready queue? P1, P3 and P4. P1 has a burst time 7, P3 has a burst time 9, and P5 has a burst time 5. P4 has a burst time 5. So which is a least one? So we know that P4 is a least one. So we'll execute P4. We doesn't have to do it one slot because we know that now all are available. We doesn't have any other option. This is the least one. It will go up to 10. Because the burst time is 5, it will go up to 10. Now P4 has been removed from the list. Now P1 and P3 is left. P1 has 7 burst time remaining and P3 has 9 burst time. So it will pick up P1 and it will execute all 7 burst time up to 17. And after that, we have only one option to execute, that is P3. So P3 will come here in the CPU and it will execute its 9 burst time and it will complete at 26. Getting it? So this is how it works. So you see, P1 will be executing from 0 to 1. At 1, because we have 2 processes available, it will compare it. And because P2 has a least one, it will put the P2. It will execute up to 5. So it is executing up to 5. After that, P4 has joined, P4 has joined, P4 has joined. It will execute up to 10. Then P1 has joined because it has the least one. It will compare P1 and P3. So up to 17, it will execute because the burst time is 7 remaining. Now after that, at last, P3 is going to execute with its burst time 9 up to 26. Now here in this case, there is no problem or a starvation. What is the meaning of starvation? The starvation means smaller process is waiting larger process to execute. And it is waiting for a longer period of time. But here we have the facility that whenever we find out the smaller process, we just execute that particular process and will remove the larger process if it is in the CPU. Now, if we'll calculate the two time, means what are the time that we have to calculate? First, we'll see the completion time. Then we'll see the turnaround time. And at last, we'll see the waiting time. Now, if we'll calculate the completion time of process P1, what is the completion time of process P1? It is 17. It is 17, right? So completion time of P1 is 17. What is the completion time of P2? It is 5, right? It is 5. What is the completion time of P3? P3 is 26. And what is the completion time of P4? It is 10. Now let's find out the turnaround time. Turnaround time, what is the, how we'll find out the turnaround time? So turnaround time is nothing but completion time minus arrival time. So what is the completion time? Is 17. Arrival time is 10. Sorry, 0. So it will be 17. Turnaround time of P2, 5. Arrival time is 1. So it is 4. 26 minus 2, it will be 24. 10 minus 3, it will be 7. So this is my turnaround time, total turnaround time. Now let's go to and find out the waiting time. Waiting time is nothing but the turnaround time minus burst time. So what is the turnaround time? Is 17. Burst time is 8. So it will be 9 is the waiting time. Then 4 is the burst time. It is 0. 24, 9 is the burst time. It will be 15. 7, burst time is 5. It will be 2. So this is the waiting time for all the processes. Now after that, we'll find out the average waiting time and average turnaround time. These two we can calculate. So average waiting time will be 9 plus 0 plus 15, it will be 24, and then 2, it will be 26. So it will be 26 divided by 4. This is my waiting time. What is the turnaround time? It is 17 plus 4, it will be 21. 21 and 24, it will be 45. 45 and 7, it will be 52 divided by 4. This is my turnaround time. Now, if we'll see, if all the processes are there in the ready queue, this algorithm work as a shortest job first algorithm. If all the processes are not available in the ready queue at the beginning, when all the arrival time is not exhausted, so we'll find out that we have to do preemption if any shorter process comes into the main memory or into the ready queue. So I hope you understood it. If you have any problem, let's do some more examples related to shortest job first. So all of you do it, along with me. Let's say we have process, we have arrival time, and we have burst time. Let's go for the process number. We have 1, 2, 3, 4, 5, 6. So 6 number of processes are there. Let's write the arrival time of it. So the arrival times are 0, 1, 2, 3, 4, and 5 is the arrival time. And the burst time is 7, 5, 3, 1, 2, and 1. So these are all different burst time related to all the processes. Now what we need to calculate here, we need to calculate at very last, we'll calculate the completion time the turnaround time, and last we'll calculate the waiting time. Okay, so all those things we are going to calculate later on. Now, if we have this particular problem, let's see how we can solve it. So as this particular problem has been solved, we'll use the same approach and we'll prepare the Gantt chart. Okay. Now let's go for time t0. At time t0, what are the processes that are available? So what are the processes that are available? At time t0, we have only process 1 that are available. Now, if we have only process 1 available at time t0, what is the burst time? Is 7, and we cannot compare it to anyone, right? So we have to put P1 into the Gantt chart. Now at time 1, we'll again see that what are the processes that are available. So at time 1, we say that P2 has also come into the ready queue. Now in that, we'll see that what is the remaining time of this particular process. The remaining time which is left here is 6. Now 6 is the remaining time, and for P2 the burst time is 5. We'll compare 5 with 7, which is the least one. So definitely we'll find out that process 2 has 5, which is the least burst time. So what we do? We do the context switching. We'll take out the process 1 and put into the ready queue. Now for that, what we do is we take out the P1 and we'll put P2 into the CPU, right? Now after that, we'll go again for 1 burst time. Why we go again for 1 burst time? Because we know that at that particular time, again, a scheduler has to check for the shorter process. Now at time T2, 3 processes are available. 1, 2, 3. Now what are the burst time here available? Here also 1 burst time has been done. So it is 4, which is remaining. Now we have to compare with 3, 4 and 6. We'll find out that P3 has the least burst time. So P3 we have to put into the CPU. So now P3 we have to put into the CPU. Now again for 1 burst time at time T3, we again check the ready queue. Now at this is 0th arrival time, this is 1, this is 2, and this is 3. Now in 3rd arrival time, process P4 is also available. Now at that particular time, if you'll find out what is the burst time that is left here is, because 1 already been done, so 2 is left here. For P4 it is 1, so we'll compare 1, 2, 4 and 6 because all these processes are available into the ready queue. So we'll find out that P4 is having the least one. So definitely P3 will get out from the CPU and will put P4 into the CPU for another burst time. So another burst time, the next burst time is 4. Now at that particular time, P5 is also available. At that particular time, P5 is also available. Now, what is the remaining time of P4? So you see that P4 has already been done. So we'll remove the P4 from the ready queue list. So we just remove it, P4. What are left? P1, P2, P3 and P4. So we'll compare in between P1, P2, P3 and P4. Now what is P1? It is 6. P2 it is 4. P3 it is 2. This already been done. We doesn't have to check it. And then last is P5. P5 is 2. You find out that this 2, 4 and 6. So definitely 2 is less, but we'll find out that which 2 is there. We have two processes which has the same burst time. So what is a tiebreaker? Tiebreaker is arrival time. Whose arrival time is less? So definitely P3 has arrival time which is less. So we'll not put P5 into the CPU. Instead, we'll put P3 into the CPU. So now you put P3 into the CPU and go for at least 1. Now at time T5, sixth process is also available. So we'll put sixth process into the ready queue. Now we'll compare with 1, 2, 3, 5, and 6. Now because 3 has already 1 done, so we'll see how much is remaining. So for 3, 1 done, so 1 is remaining for 3. Now if 1 is remaining for 3, we have how many options? 1, 2, 3, 4, and 5 options are there. Here again, we'll have a tie of process 6 and process 3. Both are having the same burst time. So we'll go for the arrival time. Because arrival time of P3 is less, so we'll pick up P3, and P3 will go again for the further for again 1 burst time, because after that it will be done. So 6. Now P3 has been done its execution, so we'll remove P3 from the ready queue. Now which is left? P1, P2, P4, P5, and P6, which is less. Now we have P6, which is less. There is no tie. 1, 2, 4, and 6. So definitely we'll pick up 1. So 1 burst time, which is of P6, it will execute up to 1, 7. Now P6 is done its execution, so we'll remove P6 from the ready queue. Now which are left? P1, P2, and P5. Let's see. P1 is 6, P2 is 4, and P5 is 2. So definitely we have to pick up the least one. So P5 will go here. It will execute 2 burst time, means it will complete at 9. After that, P5 is also completed. Now after that, P1 and P2, which is the least one. So P2 is the least one. It will execute up to 4, means it will be up to 13. And after that, P1 will come, and P1 will execute another 6 burst time, means it will complete at 19. So you can see here that how this how the shortest remaining time first works. Now we are doing 1 burst time. Why we are doing 1 burst time previously? Because we want every process will get the chance. That's why we are doing 1 processes. Once all the processes are available after 6, we can do based on the shortest job first. So shortest job first is we'll pick up the short one, we'll execute all, then we'll pick up the short one, execute all, then we'll pick up the short one, execute all. In that way we'll go, right? So in that way we'll go. And once, as I told you, once all the processes are available in the ready queue, the shortest remaining time first algorithm works as a shortest job first algorithm. Then we doesn't have to check at 1 burst time all the time. Now let's go to completion time. What is the completion time of P1? The completion time of P1 is 19. Completion time of P3 is 13. Completion time of P3 is 6. Completion time of P4 is 4. Completion time of P5 is 9. Completion time of P6 is 7. So these are all completion time. Now turnaround time is nothing but completion time minus arrival time. So what is completion time is 19, arrival time is 0. So it will be 19. Turnaround time 13 minus 1, it is 12. 6 minus 2, it is 4. 4 minus 3, it is 1. 9 minus 4, it is 5. 7 minus 5, it is 2. These are the turnaround time. Okay. So these are the different turnaround time of the algorithm. Now let's go to the waiting time. Waiting time is nothing but turnaround time and a burst time. So what is the turnaround time? Is 19. Burst time is 7. So 19 minus 7, it will be 12. 12 minus 5, it will be 7. 4 minus 3, it will be 1. 1 minus 1, it will be 0. 5 minus 2, it will be 3. 2 minus 1, it will be 1. Now waiting time will tell us that how much time a process is waiting into the ready queue. So how much time a process is waiting? Say you can see that P4 is not waiting at all. Once the P4 is coming at time T3, it get a chance into the CPU and it will execute because the P4 has an execution time 1. So it has the least execution time at that particular time. So it is executing and getting the CPU. Now for the P3, the execution time, waiting time is 1. For P6 also waiting time is 1. So in that way, we'll find out the waiting time of all the processes. And at last, we'll calculate average waiting time. And what is the average waiting time here is 12 plus 7 plus 1 plus 0 plus 3 plus 1 divided by 6. You calculate it. Average turnaround time. So what is average turnaround time? Here it is 19 plus 12 plus 4 plus 1 plus 5 plus 2 divided by 6. So it will be it is 19, 20 and 24. 24 divided by 6, right? And it is 19 and 29, 31, 31, 35, 35, 40, 43, 6, right? So these are all average waiting time and average turnaround time of the processes. So I think you understood that how shortest remaining time first algorithm works. Let's do another one, which is a gate question. Two 2007 question that we'll try to do. Now in this, it is given process number We have arrival time and we have burst time. There are 4 processes that are given. Arrival time is 0, 15, 30, and 45. The burst time which is given is 20, 25, 10, and 15. So all those are the burst time which is given. We have to calculate all those things. Let's see in the examination what it has been asked. It asks that waiting time for P2 using shortest remaining time first. The question is, what is the waiting time of P2 in shortest remaining time first algorithm? That is the gate question that has been given. Let's solve this. So we know that we require the Gantt chart for that. So we'll create the Gantt chart. Now let's go to time t0. So at time t0, we have only one process that are available, P1. So definitely we'll put P1 into the CPU at time t0. Now what is the next process that is coming? That is coming is P2 that will come next process, but the arrival time is 15. So definitely up to 15, we have to run P1. We doesn't have any choice. At time 15, we'll see what is the status. The status is now in the ready queue, we have P2 also available. If P2 is available, now what is the remaining time here? So the remaining time which is left here is, because 15 already done, 5 is left. So 5 and 25 will compare it and we'll find out that because 5 is less, so we'll go again with P1. We'll not do any context switching and P1 will continue for another how much time? Because it has only 5 burst time left, so it will go up to 5. Secondly, it doesn't have any process that are arriving before 20, so it will execute up to 20. Now once the 20 is finished, you find out that P1 is no longer in the ready queue because P1 has already finished. It will go up to the it will go into the terminated state. Now P2 is left at time 20 because at time 20 P1 is done its execution. P2 is only there. P3 is not arrived. Now because of that, P2 will get the CPU and it will execute up to, because it is 20 right now, up to another 10. Another 10 means at time t30, we'll see what is the status. The status will find out that P3 also came into the picture. Now, how much time it has run? So it has run up to 10 unit of time. So how much is left? It is left 15. So you see, we'll compare P2 and P3. So we'll find out that P2 has remaining time 15 and P3 has remaining time 10. So we'll find out that P3 has the least remaining time or the least burst time. So P3 will get the chance into the CPU and P2 will again get into the ready queue. Now P2 is there in the ready queue. P3 will execute for how much time? So it will execute another 15 minutes or 15 unit of time, because at 45 only the P4 will arrive. But because only 10 burst time is there, so it will execute up to 40. And then P3 will be gone from the ready queue and it will go into the terminate state. Now at time 40, P2 is only left. So P2 will get the chance into the CPU and it will execute up to 45. Now at 45, because P4 is coming into the ready queue, we'll see the status. Now the status of P2 is, because already 5 has been done, so it is 10 that is remaining. There is no P3, there is no P1, only P4 is there. P4 will be compared with the remaining time of P2. It will be 10. Its burst time is 15. So definitely P2 will continue. So P2 will continue for another 10 unit of time. And after that, this P2 will be terminated and P4 will get the chance into the CPU and it will execute up to another 15. So it will be 60, 70. Right? So this is how it will be done. So I think it is clear to all of you, right? Now, what was the question? The question was, what is the waiting time of P2 in shortest remaining time first? We have to find out the waiting time of process 2. So for that, we have to fill up these two columns. So we'll fill up these two columns one by one. Let's go to the completion time. So the completion time which we'll find out here is for the P1, the completion time is 20. For P2, completion time is 55. For P3, completion time is 40. For P4, completion time is 70. Now, let's go and find out the turnaround time. So what is the turnaround time here is completion time minus arrival time. So completion time is 20, arrival time is 0. So turnaround time is 20. 55 minus 15, it will be 40. 40 minus 30, it will be 10. 70 minus 45, it will be 25. Now let's go to the waiting time. So the waiting time is turnaround time minus burst time. So the turnaround time is 20 for P1. Burst time is also 20 for P1. It will be 0. 40 minus 25, it will be 15. 10 minus 10, it will be 0. 25 minus 15, it will be 10. So the waiting time will tell us that P1 and P3 doesn't have to wait for any unit of time. Once P1 and P3 arrived, it gets the chance into the CPU. But for the P2, what is the waiting time? The waiting time is 15 unit of time. Okay. So you can say the answer is 15 for P2. If it will ask that what is the average waiting time, calculate the average waiting time. So you can calculate the average waiting time. It will be 15 plus 10, which is 25 divided by 4. This is your average waiting time that you will find out. If in the examination it will be asked that find the average turnaround time. So for that also you can calculate it. It will be 60, 70, and 95 divided by 4. So in that way. This is how you can calculate whatever is given in your examination.